All right, full screen here. Looks like this is the rest of lesson set 13, I believe. So I'm going to do chunks of problems on each part of the whiteboard here. So I'll just reel Rennie the cart down the pathway, and you can pause the video from time to time, see what kind of questions are coming your way, and I'll just keep right on moving. Then I'll come back. No rush today, be able to tackle these problems and talk about them a bit, which I am assuming is probably going to be helpful because this is the second half of the lesson set, newer material you haven't worked with as much. We're going to be doing sine and cosine and tangent functions starting Wednesday in a using radian measurements. So introduction to the unit circle is something that hopefully you can watch that video and be prepared to kind of hear it again in class. I think you're probably learning right now, the more times you do something, the better you get at it. I've got a bunch of sketches, so we're going to sketch all of these calculations. Continuing to do some more graphing, getting a perspective on the solutions to all the equations on the board. And if you were to write an X and a Y in a table, and you'd be working forever. So we like to draw pictures to see trajectories and to get a feel for the totality of the calculation. Right. What happens when you put really, really big numbers in here? What happens when you put in really, really big negative numbers? What happens locally? All right, that's what we're going to be looking at. I'm going to be talking about the cosine function, one period, all entry-level discussions, and then a whopper at the end. I don't even think we have graph and logs down yet, and here I am doing that to you. But these are archived worksheets. If I have to create those worksheets right now, then I'm not making the videos. So I'm thinking the videos are hopefully helpful. I've realized that I need to make a playlist so that this becomes, in essence, a course. And that course, I hope, will take us from algebra 1 to pre-calculus and beyond to calculus, depending on how many lesson sets, but we're just going to keep building here. All right, so for years, I forgot to put the bracket around here because, well, I guess you don't need to hear this, but technically I need this all inside some kind of grouping symbol. All right, so mass of language, do you know the language of what this is asking? It's asking you to write exponential activity that you see on top of base M. Well, I see a lot of exponential activity. I hope you can see why it comes out as a 12. That's that answer. How do we get there? Well, 8, 12 means there's 4 more in the denominator. That's 1 over m to the 4th, which can be expressed as m to the minus 4. That can be expressed as m to the minus 4. Okay, I see the activity. That's what it is. Next one. Well, I don't want m squared. I don't want squaring. I want the 14th power. Now, that's on the conceptual side of things. What's this asking? It's saying, what exponent do I have to put on top of a 2 to make it m to the 14th? I think it's a 7, right? We don't want squaring. We want the 14th power, which means 7 times 2 gets me the 14th power. Yep, you can see fine. All right, these you can do in your head in a little while, but right now we're going to look at 16 and 49, 65. But right now we're looking at bringing the x over to this side. This question's about, these are the answers to a quadratic. These are the answers to a quadratic. What quadratic did it come from? Well, quadratic functions are generally set to 0. You do that more than anything else, because maybe you can factor a problem quickly and easily. So it's set to 0. Great. I don't see 0 on the right-hand side, so let's move everything to the left. What's the next step? Squaring. X squared minus 8x plus 16. Hopefully you're doing that correctly. Squaring this gets us 49i squared, which happens to equal negative 49. So what am I going to do with negative 49? I'm going to bring it to the other side and write x squared minus 8x plus 65 equals 0. Let's see where these answers come from. That's another thing we're working on. We're working on completing the square. And we've been talking a lot about these first two terms. That's a rectangle, x and x minus 8. Okay, I'm going to make it into a square. X minus 4 squared minus 16. That's the same as that. Square 16, take it away, the constant's gone, and you get x squared minus 8x. I still have 65. That's a 0. Okay, so what do? We add this and we get 49. If I bring it to the other side, it's minus 49. And I've got x minus 4 squared. Okay? X minus 4 equals plus or minus the square root of negative 49. And I hope everybody sees that that can be written with I at the end. And there's your 7I, what we started with, bring the 4 over. And hopefully you can see how you go forwards and backwards. Now, this is a non-traditional approach to solving that equation. Textbooks, just so that you can see it, would have written the x minus 4 squared as this. Nothing wrong with this method. But I think the other method really highlights inverse operations, which is so important to be able to look at something and go boom, 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 boom. Have no idea what I just said. All right. So our answers were 4 plus or minus 7i. So let's do plus 7i, make it like a conjugate, minus 7i. I always felt like that was a little hard for folks to generally see. Maybe it isn't if you underline the x minus 4 and the x minus 4. That was this part, right? And then you have what? No middle terms with that. If you think about this as entity, maybe. Well, hopefully you can see what I'm doing here. And then you got 7i times minus 7i minus 49i squared. Everything is there. But I do think the inverse operations going the other way, to me, it's a whole lot easier. That's the rule in my class. Whatever the easiest way is, we're going to adopt it. I hope it's easy. All right, so what's the easiest way to tackle this problem? I think to make columns. It's not hard at all. It's just a question of keeping track of things. Minus 5x squared times x squared is minus 5x to the 4th. Minus 5x squared times minus 3x is positive 15. X squared times x, x cubed. And I was talking with one of the students in the class. Minus times a positive is a minus. Sometimes that can, maybe, you know, as instructors of Algebra 1, we're always wondering how to help somebody who has difficulty with sign computations. Well, maybe that's it. Maybe you just say that first and then worry about 5 times 4 times x squared. I don't know. I wish I'd thought of that 45 years ago. Minus 3x times x is, minus times a positive is a minus, but I don't know where to put it now in the column. That's okay. Minus 3x cubed. Oh, that's this column. Minus 3x times x is minus 3x squared. And minus 3x, a minus times a minus is a plus. 3 times 6, 18 times x. So you got to be careful. Then just add things up and here's your answer. Minus 5x to the 4th plus 12x cubed minus 23x squared plus 18x. That's as good a way to handle that as any, I think. All right, let's continue moving down. Renee, come on. Negotiate that turn. Good job, Renee. Oh, got hung up. There we go. All right, last time I missed this board altogether in the last video. Conjugate. Okay, this level of difficulty, I hope you just write 15 plus 25i over 3 squared 9, 25, 34. All right, but where is it coming from? Oops, got to do the conjugate. The conjugate is the a plus b times a minus b situation. So I got 3 plus 5i. No middle terms now. That'll get me I squared, which is -1. So I'm getting the imaginaries out of the denominator. Now, why do we do that? Well, it's awkward having it there. Say these two numbers, 2 divided by I and I divided by 2. Which one do you have a better feel for? I'm not sure what that means. Okay, divide 2 by imaginary number. Take an imaginary number and cut it in half. I think the latter has a better feel for size. So 5 times 3, well, there's your 15. 5 times anticipating the conjugate. 5 times 5i, 25i. What happens to the middle terms? The middle terms cancel. What were the middle terms? The middle terms, well, what were the non-middle terms? 3 times 3, 9. Minus 5i times 5i is minus 25i squared. So this is what's in the denominator, and I'm saying it's that number, and I hope you can see why. I squared changes the sign of the coefficient in front of it. There's that answer. All right. Now, there's a rule of 4 in the textbooks, but I don't think anybody's going to remember that after 2 years or something, but you might remember. You might remember that I squared is -1, which means you can build your answer off of I squared. 9i squared 2 times gets me to 4, times 1 more I gets me to 5. And what is I squared? I squared is -1. So whether this is an odd or even, doesn't get determined by the parentheses. It gets determined by cutting that number in half. Sometimes you'll have the original exponent. Cutting the original exponent in half gets me that number with a remainder. Sometimes you won't have a remainder. But now I see -1 times -1. I see this as positive 9i. And once you start seeing it, then you just write your answers. All right, so I'm not going to do, let's do one more. It's fairly new. So let's do 9i to the 47. I'm seeing that as 9i squared 23 times I. That's odd. So -1 an odd number of times is going to remain. It's going to remain negative. So my answer is minus 9i. You can start doing those in your head with practice. Okay, where you don't have to write anything down. You just say what the answer is. All right. So the reason I did mental math, it wasn't why I did mental math in the last one. I had time constraints. But I like to see mental math on this. If I see more writing than what I'm going to do, it actually gets in my way of seeing if you did a correct statement. Add 5. Divide by -2. 3 to the. That's the inverse of log base 3 of is 3 to the. Add 4. Put the number in, see if it works. 5 minus 4 is 1. Erase that now. What is the exponent you put on top of a 3 to get a 1? 0. -2 times 0, 0. Okay, bring the 5 to the other side. Yeah, my answer was negative. I forgot the original question. I shouldn't have erased everything. I hope I didn't make a mistake, Yasser. Back me up, buddy. All right. No, I didn't do that wrong. Bingo, bango, bongo. Okay, now, once you get this down, you don't need parentheses for bingo, and you really don't need parentheses for bongo. But it's useful, I think, for quite a while to make sure you put bango in parentheses. All right, so what do we have? I'm going to do parentheses for everything. 2x plus 1 times 2. 4x plus 2. 5 times 5x plus 3. 25x plus 15. Over 5 times 2. I'll just write 10. All right, now I don't need this parentheses really. And this minus sign really means -1 times what's in parentheses, which means that 25x becomes negative, and so does 15 becomes negative. Now I can put like terms together, 4x minus 25x minus 21x, 2 minus, no, sorry, I got rid of that. 2 minus 15 minus 13, and that's divided by 10. Now, do I have a friendly number up here that I can work with? let's see, what would I pick? I don't know. 2 maybe? Keeping this small would be nice. Shoot. All right, so any number that you plug in, if I put a 1 in, I've got 3/5. This shouldn't be bad. 3/5. If I put in a 1 over here, I've got the number 4. So what do I get? I get minus 20, minus 17 over 5. If I put a 1 in here, it better come out as minus 17 over 5, or I made a mistake. And it doesn't look good. I don't like what I'm looking at. But anyway, maybe it's reduced. So put a 1 in, minus 21 minus 13 is minus 34/10. Oh, I'm happy now. Dividing by 2 gets me minus 17 over 5. Didn't see that initially, but it looks good. All right. Now I've got at the top here, factoring the sum and difference of 2 cubes. Well, I haven't shown you that yet, so I'm going to show it to you now. And I'm sure in the playlist, if you type that in, you'll get 5 to 10 practice problems somewhere. I just don't remember how long ago I did it, but I know it's there somewhere. So let's look at a couple of cubes, a cubed minus b cubed. That's really the textbook form of, formula. Difference of 2 cubes. Let's look at, how about 27 minus 9? Oh, minus 8, excuse me. So often I do quadratics. So 27 is a cube. Enough, right? It's a 3 by 3 cube. 8 is a 2 by 2 cube. Let me get just anything up there. 2 by 2 cube. That's all you need are the cube roots. You got the cube roots, and you remember the jingle, you're all set. So I'm subtracting, so there's my 3 minus 2. Remember, I'm trying to get this thing to equal 19, which is what 27 minus 8 is. I'm done looking at the picture. I just have to remember a few things. I've got the number 3. What I don't have is the other 2 3s. So that's 3 squared. I've got a 2. I don't have the other 2s. So that's at the end as a positive, always positive, 2 squared. Okay? Now, this is the number 1. Right now I've got 9 plus 4 is 13. I'm missing 6. I'm missing plus 6. And now it's 19. I wonder where I could get that 6 from, considering I have 3 minus 2 here. If you said multiply, you'd be right, and change the sign, you'd be right. So that's how you can do, that's the framework for factoring, writing products for cubes, sums or differences. We don't write the sum of 2 squares out as a factoring product, but the difference we do. Well, in this case, we get both. Let me just show you the cancellation of terms here, because it's something you can see. Let's change this to 9. Let's change this to 4. And let's do 3 times that parentheses first. Well, that's 27 plus 18 plus 12. Now let's do minus 2 times this parentheses. Minus 2 times 9, minus 18. Minus 2 times 6, minus 12. It's got a little conjugate feel to it. Minus 2 times 4, minus 8. All right, let's get rid of the middle terms here that cancel out of the problem. And I think I'm looking at 27 minus 8. So you try a cubed minus b cubed right now while I erase. A cubed minus b cubed. I know the cube roots. A minus b. I think I need a squared. I think I need the product, ab, and I think I need b squared. And there we have it. Now they can get more difficult, like this one. And you haven't really worked with that too much. But what's another way of writing the cube root of b squared, of b to the 12th? What's another way of writing that? Well, I hope you say b to the 12 over 3. I think you probably just said b to the 4, and I don't blame you. But that's another way of expressing a cube root. So, does 3 fit into 12? Yes. Does it fit into 9? Yes. Do you see cubes here? I hope you recognize it as the sum of 2 cubes. So, I'm going to write, in this case, a plus. What's the cube root of 125? 5. What's the cube root of 8 to the 9th? Well, remember, you could have written the cube root of a to the 9th as a to the 9 over 3. That means cube root. It fits in nicely as a to the 3. And we go, I'm here, 3b to the 4, if we apply the same logic. This parentheses is built off of this one. I have one dimension. I need the other 5a cubed times 5a cubed, which is 25a to the 6th. I hope you can see 3 and 6 is 9. And if that's a positive, I need those cancellation of terms. So we'll make that one a negative. It's the product. What's the product of 5x plus 3y? I hope you would say 15xy, right? If I made this a product. Okay. So what's this product? The exponents don't change. So 5 times 3, there's our 15. And I have a to the 3 times b to the 4. And then I square the last term, 9b to the 8. Just takes a little practice. And now we're factoring the sum and difference of cubes. All right, let's see, where are we at? Get rid of this. All right, so I asked piecewise. Well, this is a V shape. And from left to right, I'm going up and then going down. So here's Alfred Hitchcock again. So looks like there's symmetry. So the rate at which I'm going down, I can see is -2. I think I'm going up at +2. So on the left side, I'm going up. I don't need absolute value symbols anymore. It's a linear branch. This is a branch. Okay, so I've got 2 times, hang on. Yeah, colleague over there, but he realizes that I'm doing a video. That's right. You want to be on? You want your pick? No, okay. X plus 4 plus 6, but it stops here. It stops going up at some location, and we're working with X's. I wonder where it stops. Oh, it appears to stop at -4. Yeah, if I pick a number bigger than -4, like -3, that's 1 unit of change. -3 plus 4 is +1. The absolute value of +1 is 1. And what if I pick -5? It's a number smaller than -4. Well, I get a sign change, but the absolute value wipes out that sign change and makes it positive. So that happens at -4. So when I'm less than -4, I'm on the up branch. When I'm to the right of -4, that's the way to say that. And it doesn't matter where I put the equal sign, but I got to have it covered because that coordinate exists. So those are the branches. Now you can always use the branches to solve for -20. In other words, you can come over here and just erase that. No, you can't actually get it unless you got a teleporter or something. Setting it to -20, and you can do that quickly, right? You subtract 6, -26, divide by 2, which is -13. Now, I'm going to circle that. If I did it for this one, and I set that to -20, then subtracting 6 -26. But now when I divide by -2, I get +13. Ah, okay. And let's continue. Let's subtract 4. My final answer, subtracting 4 is -17. And subtracting 4 here is 9. So let's get down the number line. Let's look at -13. And let's look at 9. Okay. And what is the most important X value in this problem? Where the sign changes occur. And the sign changes, I'm going to put a circle here. The sign changes occur at -4. Okay. Let me make sure I didn't make a mistake because I'm not seeing something that I thought I'd see. No, I definitely made a mistake here. So let me see what the heck mistake I made. It's probably on this one. Because that's 13 units of change. So 13 units of, -17. I knew I did something dumb. There we go. All right, so how far is it from -4 to 19? +13. How far is it from -4 to -17? -13. Every step in an equation really signifies something in the inverse process. That's what I was hoping you'd get from lesson 12. Start seeing that. All right, so I have two solutions. One of them, keep them on a number line. One of them is 9 and the other is -17. That breaks this up into three intervals. Interval A, interval B, and interval C, and two other considerations for what works in the equation. I want to be less than -20. Okay, so I want this function to be less than -20. All right, well, it was important to find out when it was equal to -20. We've done that. Now, for starters, this is called, it's basically a sign chart. But we're going to write true, false, true in those intervals. And first off, I hope you see that if you use -17, it equals -20. It's not less than. So these numbers do not work, and you'd have to check them in future problems if there's an equal sign there. It's not there, so we only have the considerations of the intervals. Let's pick a number. I'll put 1,000,000 in here. -2 million plus 6. Is -2 million less than -20? Well, here's -20 on a number line. I wonder where that is. Oh, I think it's way out here. I would say that's true. What number? Oh, I picked it this side. Million is bigger than 9. Okay? And what you're going to find is it alternates. You're going to find that to be true. I'm just telling you that. We got a lot of work to cover. There'll be enough practice problems out there where it's not so simple just to write the answers. And we're going to look at interval notation. Now, here is something you did in grade school. Okay, interval notation would say that that is 7 to infinity. And I can't bind infinity. Bounded. Now, if I close this, then 7 works. We use a bracket. Okay, so what's the answer down here using interval notation? Interval notation, I can see that negative infinity until I get to -17, and -17 doesn't work. Union also, there's another interval that works, 9 to infinity. All right, that's the same thing as open circle this way, open circle that way, and you got to probably use the word or. All right, you can't use the word and here. That was something you might have studied, conjunctions, disjunctions. Okay, all right, next 4 problems. We're going to start doing unit circle work on Wednesday. Not going to spend a lot of time on that right now. I'd like you to watch the introduction to the unit circle, and then we're going to dive into that head first. And let me tell you something, it's not that hard, and most students get it within a week's time. The manipulation of this will happen. Okay, it might feel a little daunting at the start, but watch this video. Let's get the conversation started. So these are right triangles I've been drawing in standard position. We've been mostly drawing them in quadrant 1, but we're going to start drawing them in other quadrants. X is 4, Y is 5. How about I make that 4, I make that 5. That looks to me like it's a little bigger than this. So I got an angle a little bit bigger than 45 degrees. We'll call it angle A. And I'm looking for eventually the sine of angle A. I don't know where I put it, but I'm sure I must have asked it. Well, first we have to find the hypotenuse. 16 and 25, so square root of 41. All right, so what I basically did was drew a picture. I squared 4, I squared 5, and Pythagoras says that adds up to 41. Well, it's not Pythagoras that said that. I think the Babylonians did it thousands of years earlier. And Pythagoras didn't even do it. I think it was one of his students at his school. At least that's what I heard. But I was around back then, but I wasn't in that neighborhood. All right, so there's 90 degrees. There's my angle A. Hope you can see what that's called. It's called the square root. Square root of 25, 5, square root of 16, square root of 41. So the sine of angle A, we'll just stop there, is opposite side divided by hypotenuse. Okay? All right, so that one's done. The element of 8. We're learning these numbers, e to the numbers. We're doing e to the numbers so we can get to the rules of logarithms. Rules of logs. So getting good at this will allow you to see the rules of logarithms, the rules of logarithms a little better. Okay, well, I know e to the 0.7, the banker's rule, e to the 0.72. And if it's an exponential function, we're going to get 2 times 2 times 2 times 2 as soon as I put an x there. Roughly, an approximation. All right? If I want a better approximation, I go to the calculator, I find the button, the natural log button, I put a 2 in, and it would have told me, I know what the first three numbers, I think the first two are 0.69. I'm not sure. I think it might be a 0 after that. I'm not sure. But that's a closer approximation. I think it's 0.4, but I use 0.7. It's easier to work with. We're just trying to get a feel. So let's do it organically. 8, 2 cubed, 2, e to the 0.7, to the 3, e to the 2.1 is approximately 8. So what's the answer? Just the exponent. That's all we're looking for. We're looking for the exponent. So you put 2.1 down, I'll be happy. All right, I'm just going to do what you're going to see in the video. I'm going to start with pi. That's the top half of the circle. I'm going to break it up into 6 parts. I need 11. I need the bottom half. Boom. Can I do that? That's a little higher. So I'm just going to do it where I know they belong. There, that's a little better. So if I count from here, that's 1 pi over 6. That's 2 pi over 6. That's 3 pi over 6. Right? Pi over 2, we work with that. You're going to end up here. And if you draw a perpendicular, you got a right triangle. And we're going to pretend, well, I'm not going to pretend it's a unit circle. So the hypotenuse is 1 no matter what quadrant we draw it. And if you ask yourself, pi over 6 is in degrees? Well, we know pi is 180 degrees if I start from here. So pi over 6 then, in degree measurements, is 180 divided by 6, which is 30. I'll do the introduction to the unit circle right now, just finish it off. Here's an equilateral triangle. Okay, that's 60 degrees, that's 60 degrees, that's 60 degrees. All right, let's call this 1, 1, 1. All angles are the same. And we want to get a 90 degrees, so why don't I cut this triangle in half? Okay, cut it in half. Okay, well, that's still 60, but now that's 30. And I also know that's a half. Well, what's Pythagoras say? Pythagoras says 1 squared is 1. 1/2 squared is 1/4. I think I'm going to stop saying Pythagoras says. Let's say the Babylonians said. Maybe somebody else did it earlier. I don't know. But I do know that the sum of the smaller sides of a square equal the largest across from the hypotenuse. So that has to be 3/4, which means that that's the square root of 3 over 4, which is root 3 over 2. And that's on your memorization sheet that I handed out on day 1. Probably didn't know why I was asking you to learn it. Maybe you know now. Right, so, what's opposite 30 degrees? Opposite 30 degrees is a half. Well, this is a reference angle of 30 degrees. Pi over 6, 30 degrees. The next one, 30 degrees. The next one, those are all reference angles for, well, probably misspoke just then. But hopefully you can see, we wouldn't say 3 pi over 6, we'd say pi over 2. We started working with that even before we started working with the unit circle. So that's what this video is about. Like anything else, look at it 4 days in a row, 2 minutes a day. 4 days from now, 8 minutes of practice. It's a whole lot better for you than 8 minutes of practice on day 1. Spread it out, consider short periods of consideration, let the brain process it, you'll be fine. That's been my experience. All right. So we got a lot of governmental agencies in the news these days, so I thought I'd throw you the CIA. So how would you solve this quadratic for t? What values for t can make that 0? Well, I hope you say minus I, plus or minus the square root of I squared. minus 4 times C times A, CIA, all over 2 times A. No, 2 times C. All right, so this is just a little strengthening of your memorization skills, making you work a little harder than minus B plus or minus B squared minus 4AC over 2A. Yeah, I have a little jingle for that, which some teacher said somebody else taught her when she was a little girl. Boy, there's somebody else out there that came up with the same song I'm about to sing. Don't be iffy, just, looks like a J, be squarely, for a certain, aimless, double rhyme, ness. Aim, oh, the double is over here. Aimlessness. I know, pretty corny, my apologies. All right, so I'm about to make a video on this problem. And I'm going to call it measuring sticks. I'm not going to talk about it right now. We're just going to sketch this. This is point slope. So let's see if you get the point. Boom. I see 1, -5. And I also see a function going up. So I can write this here. 1, -5. I have a location. I'm going, gosh darn. All right, I'll put it over here. You'd think I know by this time. All right, so I'm going over 7. I'm going up 10, something like that. Brings me to a new location. I think I can add 7 to 1 and call that 8. And I think I can add 10 to -5 and call that 5. How many points does it take to graph a line? 2. I've connected them. I've shown the arrows. That's all I can say. Point slope form. So I put a point on the board. I put a slope on the board. 2x squared. Okay, I got to cup shape up. Okay, do you know which side the y-intercept is on? I know it's on this side, 0, 7, but if you're not sure, minus b, 16 divided by 4. That's our x value. And I do believe 0 is to the left of 4. I looked at that, I'm on the downside. All right, so I wish I had something this is an x value. I wish I had something that gave me the y values for an x value. Oh yeah, here it is. Oh yeah, my y values come from using x values. I'll use the number 4. And if I do, I got 16 times 2 is 32, minus 64 plus 7. I've got minus 32 plus 7. I've got minus 25, and I'm done. And then I'm happy to see 2 checkpoints on my next test. Oh, that's a whole lot easier than it was day 1. All right, just now, most everybody's got it conceptually. You just got to be careful with your minus signs and stuff. I see -5 gives me the square root of 0, and I can't have square root of negatives. They're not on Rene Descartes. I don't see any negative numbers on you, Rene. Yeah. So, -5, 1, -5, 1. I see a positive, so I've got slow, got deceleration, if I can use that term. And I just need one other number. Maybe we put a 4 in. Maybe that would have been best for you, a 4. So a 4, let's call this a 4. A 4 gets us 3 times 3, 9 plus 1, 10. I have a frame of reference now. I'm a big fan of 25, so I'm going to plug 20 in. That gets me 15 plus 1, 16. 16. Well, this is a jump of 9. I got to go up another 6 units, so 2/3 of this, 2/3 of that distance puts me at about here, I think. Maybe I should have drawn this a little differently, but anyway, I don't like what I just did, but it doesn't matter. I've got 16. I think I got the altitude well. I don't think I got my horizontals matching up too well, but that's all right. That's worth 2 more points. You're not going to spend a lot of time trying to, we're not on graph paper here. So that's fine. What else we got? I see an exponential function. I see a jump of 6. I see half of that 3. That's what I'm seeing. I'm seeing exponential decay headed towards 11. Right? Because this is disappearing. 6 times a half is 3. A half of 3 is 3 halves, so on and so forth. So it's going to head to 11. So I can see my y values now. 17 is this y value. If I pick the correct x, this one is 14. If I pick the correct x, that's 14. And what do I want? I want some x's there. I don't even have any. I erased it. That was very dumb. So we'll make some up on the fly. Let's go x minus. I like the years. How about 1907? That was a good year. Yeah, I remember I went to the 3-county fair in Northampton in 1907. Yeah, and let's go, how about 100 years later? All right, so 1907, 2007. And if you're you got time on a test, check it, see if it works. 2007 minus 1907. 100 divided by 100 is 1. Well, 1 half to the 1 is a half. Half of 6 is 3 plus 11. You can see how it works. Take the time to do that. Okay. Y equals 3 to the minus x, which is the same thing as 1/3 to the x. All right. Now, a b to the x plus c is the generic form for exponentials. We're missing the a, which in this case has to be 1. It's just not written. Here's our exponent, and c must be 0. All right, so 3 to the minus x, I got a jump of 1, then I jump of 1/3. Then I'm going to get a jump of 1/9. Okay, let's just cut to the chase, make some room for myself. So y equals 0 is what I see. Every exponential function has a constant associated with it. If you don't see it, it's understood to be 0. The decay, let's call this 1 unit, then I can really show some change. That's 1, that's a 1/3, and that's a 1/9. I hope you can see we're headed to 0. Okay, what do I want my numbers to be? 0 and 1. Okay, so I can see if I put a 0 in, 3 to the 0 is 1, 1 times 1 is 1. 0 gets me 1, that's a y-intercept right now. If I put in a 1, I get 3 to the negative 1, which is 1/3. So a 1 gets me a 1/3, so on and so forth. That's enough of that for today. As long as we have a conversation, it only took a minute. Once you learn something, then you graph that in 10 seconds or less. That's what you're in the room for. I see V shape down. I see 6, 7 as the vertex. Which side is the y-intercept on? I hope you look at the x, right? Because it's all about x's. Y-intercepts are all about x being 0. So it's on this side. If I put a 0 in, I get minus 12 plus 7 minus 5. Okay. On this side, I have positive slope. How do you get from 7 to minus 5? You go down 12. How do you get from 6 to 0? You go down 6. That slope is positive 2. And this is referring back to the piecewise function a few minutes ago. And then if that's a 0 and a 6, then this is 12 negative 5. How do you get from 7 to negative 5? You go backwards 12. How do you get from 6 to 12? You go up 6. Hopefully you can see why that slope is negative 2. Okay. Now sinusoids, sine and cosine functions look like this. I'm going to consider the sine function. The sine function is all about opposite, right? And in a unit circle, the opposite is the height. And I see pi over 2, and that's where my height's biggest, 1. All right, so I'll start here, and I will erase this, and I will erase this. Now, why did I do that? Because I spot 3 pi. Remember, a little while ago, we said that's 1 pi. Halfway around is pi. That's 2. That's 3. I'm sorry. That's 2 pi. That's 3 pi. Okay, so 3 pi is 1.5 revolutions. This is 1 revolution before I start repeating. So that's 1.5. 1 pi, 2 pi, 3 pi. So I am going to name that place. I'm going to name this place, but remember, this is a sine wave. I see 1970. That's key. If I put 1970 in, I get 0. 0 times anything is 0. I get pi over 2. What's the sine of pi over 2? 1. Now, 1 times 5 is actually 5 units above 20. That's the center. 5 units above 20. This is going to be 5 units below 20. And I want to throw what number in? 1970 to, well, 4 years later. So this is going to be 1974. So if I put 1974 in, minus 1970, I get 4. The 4's canceled. I'm starting at pi over 2. I'm going to go 3 pi. There's 1 pi, 2 pi, 3 pi's down here. If that height is positive 1, intuitively, I hope you can see why that's negative 1. Negative 5 plus 20, there's your 15. Now, you haven't even done the unit circle, so don't worry about trying to figure that out right now. You're probably not going to be able to. Maybe you can. Maybe you're all set with it already. I don't know. Some students are already graphing them correctly, but I'm sure the conceptualization is going to take some time. Exponential function, another one of these a, b to the x plus c. And I always want this, no matter how complicated that is, if I make it a 0, I get 1, which means I'm going to get a plus c. And if I make it 1, then I get ab plus c. That exponent becomes 1, then I get b times a plus c. ab plus c. All right. Yeah, I think I actually archived this and I use 0 and 1. I really like 1.1, but let's stick with the 0 and 1. So I see the constant 9. E is above 1, so I see exponential growth. I put a 0 in. If I put a 0 in, I get 2 plus 9 is 11. And I ask the question, how far is 11 from 9? 2. Oh, must be a coincidence. And if I put the number 1 in, I get 2e plus 9. When I put a 1 in. Well, okay, e is 2.71, so 5.7, 5.72 plus 9, 14.72, something like that. In other words, you get a feel for the fact if that's 2, then this is 2 times 2.71 on top of 9. All right, you all guys getting a little tired here, so just going to keep moving. Probably should have said more about that. There's rapid fire 5, how to graph e to the x, rapid fire 5 in the exponential log playlist. You can get down to about a 4-second process, graphing e to the x. I bet students come in under 5 seconds on graphing those. So it depends how much time you want to spend. Cosine measures width on the unit circle. Biggest width you get is 1, smallest is -1. We generally start our trip around the circumference of the circle there. I've not moved at all. And then I go, I go around the circle and I'm back there in 6.28 radius lengths. There's 1 radius length, there's 2, there's 3, 3.14, 4, 5.7, I think, something like that. I forgot what it is. But anyway, 6.28 radius lengths. All right, so if I just want 1 period of the cosine function, then I ask the question, I'm over here on the circle, what's the width? I hope you say 1. So 0 gets you 1. What happens to the widths as I start drawing triangles now? Well, that width, which wasn't drawn, that width gets smaller. So my widths are getting smaller in the first 90 degrees. And what's the width straight up and down? It's 0. So in the first 90, we go to 0, and then we just draw a sine wave, and we come back at 2 pi. We come back to 1. Okay, so the range of the cosine function is from +1 to -1. And if I want to increase the range, well, that's what we call amplification. multiply it by 5, and now I'm 5 times bigger, so on and so forth. All right, just trying to put some initial thoughts in the head so that we can get to the unit circle and start doing some trig. Be nice to go into a calculus class if I asked what's the cosine of 17 pi over 3. All right, let me give you that answer. So 12, 5 pi over 3. I think it's negative, I think it's positive 1/2. But I'm getting towards the end of a worksheet, so let's just check it. We did it before. So I'm going to break this up in 3 parts. 60-degree angle, and heights are √3/2, and widths are 1/2. And that's a 1. That was a triangle we did a little while ago. So 12 pi over 3. I think I would have done 18 pi over 3 would have been easier. 18 pi over 3. So I made a mistake before. 18 pi over 3 is over here. So that would have been, no. 3 goes into 18, 6 pi. I was right, over here. So 17 pi over 3 is down here. And there's our positive 1/2. All right. I shouldn't do that to myself when I'm doing this many problems. All right, I see B. Ln, so that's base E, so it's the inverse of growth. I know that if I drop in something that makes a 1, B plus 1 unit to the right, I get the ln of 1, which is 0. So I'm going to get C. That happens every time. And I know that if I make this the same as the base, if I want to make that the same as the base, then I do B plus E, which means I got the ln of E, which is 1, A plus C. And that was just a challenge at the end. And it was meant to be followed. I didn't spend a lot of time with it, but that's the process that we're trying to learn for all numbers. All right, so that's that. I'll post this now. This is the second half of, I think, just this was the worksheet from Friday. All right, yesterday. All righty, big snowstorm coming. Toodaloo.